let me start with a little bit of context. When we are speaking of networking in Ethereum, there are a bunch of things there which we are dealing with, and we are doing improvements on all of these. And when we are thinking of scaling, any of these can go bad, and any of these can be the bottleneck. But today we will focus more on these things. So when we are speaking of low latency, we are speaking of block diffusion, attestation aggregation, and block dispersal. For example, in block dispersal, what we have sharding and data availability, and what we have is kind of, we are just doing partial delivery. So the nodes are only receiving part of the actual data, and this is, we are optimizing bandwidth, right? With SpeedDust, we are going down to 12% of the usage. With FullDust, we are going down to, I mean, these are theoretical numbers, obviously, and a bunch of overhead. For validators, like 1.5%, and for someone just sampling, we are at 0.1% of the data that they are getting. And in FullDust, we're already including a bunch of techniques to do with low latency. Okay, changing sort times. What we are doing there? We are kind of keeping the throughput the same. Transaction per second or whatever per second is typically same, but we are getting a better granularity in the system. So, for example, we are getting shorter inclusion delays. If you have a transaction which is sent to the mempool, it just gets a chance to be included faster, and other benefits. And we all know that this requires better diffusion latency. So we already got to gossip survey improvements, and well, part of the gossip survey improvements that we are doing are bandwidth efficiency related, less duplicates typically. Some of them are about better diffusion latency, and where we also want to keep the protocol robust, yeah? And I was drawing that nice triangle there because people like that, because that represents that you have to make compromises and trade-offs. And but I think there are some free lunch here, others are compromises. Unfortunately, triangle is not always the best model. We also have privacy, and I think we could, if we think more, we could add other dimensions. So yeah, we have to take compromises, and different techniques achieve different things. So part one. We all know propagation speed is the problem here with slot latency, right? So this is a measurement we did in 2023 on blocks. How we read this to make it difficult. This is a logarithmic scale, but this is kind of delay. Here you have 4 seconds, and these are different size blocks. So this for small blocks, everyone is happy. For large blocks, borderline-ish. This was the situation. Well, since then we developed a bunch of low latency peer-to-peer techniques. I call them the low latency peer-to-peer toolbox, and I want to speak of this toolbox. So what are in the toolbox? Well, there is one thing which is kind of an obvious choice, which is segmentation, or sometimes we call it chunking. It's just about the fact that we are using gossip sub for something which was not meant to be, like large messages are you just don't send large messages like this. If you do large message in a peer-to-peer network, you are chunking it. That's the way to do it. And you gain latency. So there's a thing called store and forward delay, which is if you have multi-hop, you are always getting the whole message, and then you can forward it. If you have smaller chunks, then you can fast forward. And we are doing it. So we are going in this direction. We have this thing called now cell-level messaging, or partial messages, which is adding some message support. I think we will also have something like substream support. It's not something there yet. This, however, requires verifiable segments. So if you want to do this, all the segments have to be kind of verifiable somehow. We have it with KZG in DAS, but we need something there. Okay, our second tool is, I was putting it together, is scheduling and prioritization. So if you assume that you are bandwidth limited, and you should assume, otherwise the game is easy, just send it to everyone and it's done. So if you assume you are bandwidth limited, you have to make choices. Who am I sending it to? What am I sending? And this is the scheduling and prioritization, and the current gossip sub is quite naive in this. So we were introducing things like batch publishing, and that's already in some of the clients. And you can do things in forwarding scheduling parity. And I was putting quick in this category because what we achieve with quick is very related. So we have independent streams with quick. We can prioritize between them. And then we can also do with quick something which is unreliable transport. So I'm sending a piece, and then it's already timed out and I don't need it. I don't have to resend it. I can send something else instead of that. So this is kind of scheduling and prioritization as part of our toolbox. Next one, encoding. We love this. So encoding, read form encoding, fountain codes, random linear coding. These are techniques that we usually use in communications, and it was not really used here. And what you achieve here. So you achieve here, basically what I call it typically, you are cutting the tail of the delay distribution. So there are those cases when the delay becomes high for some reason for someone, and you are trying to chop that off. So in the sense that those are getting it faster. So instead of waiting for a timeout and asking for a missing piece, you are just getting it. Getting an encoded piece. This is for error correction. Or instead of sending duplicates, you are sending another piece, which is a useful piece because of the encoding. So what you achieve is kind of, you are reducing the delay because we are cutting the tail of the delay distribution. Okay. We can use these summon codes, we can use fountain codes, we can use random coding. There is a small note there that this is adding coding delay, encoding decoding delay. So you have to be a bit careful, but it's a nice technique. Then we have network coding. Network coding was there since 2005. It has been there for long. We might apply it. It's basically about, in the network, we can do recoding. And with this, we can basically achieve a situation where anything we send becomes useful. So there are no duplicates, in the sense that whenever I'm sending something to someone, he can use at least a part of that. It comes with compromises. It comes with the compromise that then you have to collect all the pieces before you can get anything useful out of it. But it's a technique which combines very well with random linear codes. You can try to do something similar with other codes. It again adds coding delay, but it can speed up and make more efficient our network. Okay, so we had 4 tools. Oh, we have more. So we have typical tools here. One is the kind of the overlay optimization box. So you have this graph overlay, and we do it sometimes random graph. And then you can imagine that the data is ping-ponging back and forth through the ocean, and that seems like useless. There are questions on whether that's actually useless or not for the robustness. But you can do latency-based optimizations. Again, you have to be careful because you are reorganizing the graph and you are losing glass properties. You might have a bigger distance in the graph, so more multi-hop and so on and so forth. But we are working on this. This is this WFR gossip that we are working on now, so we are working on a variant of this. Okay, that was number 5. Number 6, I should have put the numbers, is kind of traffic pattern specific optimizations. So we are using Gossip Sub now for like a generic tool, which is good for everything, and it's not. So we have different use cases. When you are sending the block, these are isolated broadcasts of large messages. When you are sending attestations, this is concurrent broadcast of small messages. And there is also a question why are we even broadcasting those, which was also raised by others. And I could continue the list. So for each kind of use case, you can tune the protocol and get better numbers. So the numbers. And you might have noticed that I was not putting numbers. So I'm showing 2 things here. One is this is from the Explorer, from the labs, from PandaOps, kind of similar to the test 2023 test that we were doing. It's just a much nicer interface and much more modern. So what you see here is one block. And one block which was first seen after 1.72 seconds. So maybe someone was doing delay games or whatever. Anyway, let's assume that's when it was sent. And then you see how it was diffused. And the different curves are different continents and nodes at that continent. Anyway, what you see is that after 2.2 seconds, everyone had that block. And that block happened to be a 65 kilobyte block. and I think there were also blobs, and actually 7 blobs, and I think that's included on those curves. So this is fast, right? That's cool. That's positive. It seems we can do much faster. On the right, you see, actually this is from yesterday evening, when I was running my experiment from 2023 on attestation propagation. So this is my node getting all the attestations for a given slot. And this is filtered for those which were missing slots or slots which were very bad. So until 4 seconds, nothing happened, and then at 4 seconds, things started. And one thing you can notice is that there are good cases where it's very fast. Other thing that you can notice is that they are kind of all different. And this is the problem with these things. If I would draw 4 blocks one after another, they would be all different. And it's really hard to say, like, this is the mean behavior. This is the. It's really hard to give guarantees on these things because there are so many variables in the system that it's hard to understand. And actually, even if you are simulating this, it's really hard to get to the point where you can say, I have 10 to the minus 6 that it won't go above 4 seconds because you just can't capture all the complexity of the system. Okay, but I mean, the numbers are nice. We have these small numbers. So let me go to the part 2 of my presentation, which I was calling Is Propagation Speed a Problem? And here I want to play a bit a naive view of devil's advocate. And for that I have to go back a little bit to how a protocol is working. So there's a sender sending a message, there's a receiver receiving it, and then it's sending an acknowledgement. And then when the sender is getting the acknowledgement, it's deciding whether it has to resend because it was not getting the acknowledgement, or it sends the next message, right? This is kind of how a simple network protocol works, the most simple. But then you realize that you have to choose this timeout, and when you're choosing this timeout, there is some uncertainty on how fast the message is propagating and how fast the acknowledgement is propagating. So you have to add slack to it, right? And then you have to choose a timeout which is bigger. Stay with me. And then you realize that message size also matters. Like, bigger the message, bigger the time. You need even bigger timeout. So the question is kind of how we define the slot when we are speaking of this slot time. And here I'm just kind of wrapping out this figure and transforming it into a network instead of just a simple communication. So we have the builder, it is sending the block. And then in this communication, which is not to a node, but to all the testers, we have to add a bunch of slack. The worst case size, the worst case propagation, multi-hop uncertainty, and you can go on. And then these attesters are sending out attestations. And then that's again a multi-hop propagation with aggregation. You have a bunch of slack there. So the worst case becomes like huge, right? So the real problem is that we have to deal with this third case because it's too hard for us to sacrifice a block. And this is kind of my thesis here, that we should make this much simpler. We should make it simpler to sacrifice a block in the system, and then you can scale. And actually, this thing that I've shown to you at the beginning, this we call stop and wait, and this is from the Stone Age in networking terminology, like from the 60s, or I don't know. And then networking was evolving, and we developed a bunch of techniques. So we know how to parallelize. We can send a bunch of messages on the fly, and then we have something which is called selective acknowledgement, which is a bitmap of which one was acknowledged. And then you see here bitmaps. And then you can think of, oh, maybe I can merge bitmaps and that helps. So this is something kind of delayed execution. And then in networking, we know how to do capacity exploration. So how many messages you send. We know how to scale this up and scale this down. And we do flow and congestion control. And then we also do something like timeout tuning. Like we also know how to play with this. Do exponential backoff, which is I'm extending the timeout. And for example, Vitalik has now a postulated exponential backoff, I think. And then we know how to do further correction. So we anticipate losses, we do a bit of encoding, and then we don't have to well, we don't have that many zeros, or even if we have 2 zeros, it doesn't matter because we are encoding and we are just going forward fast. And then we know how to pipeline. So it's not that we have to always wait. We can just pipeline after it. So I don't know how to map these things into blockchain space. I'm just saying that there's latency which will not go away from the system. And in networking, what we do is we are working around it. And sometimes I feel that here we are trying to do this worst case thingy, which doesn't allow us to work around it. So I see some ideas to work around it. And maybe we just need to work around it. That's all. Thank you. Questions?
Yeah, maybe just on this last point, you mentioned that we do this worst case thingy.
Yeah.
Yes, and I mean, I guess that sounds somewhat political, I guess, between working, being able to work around it or not. Maybe you could say more on.
Yeah, so currently the cost of throwing away a block, which is quite big and lots of effort, and then the network is doing lots of effort to make sure that it's actually checking and everything, is so much that then you don't want to throw away. And if that means that you have to tune your delay such a way that you have, with basically 100% you are not throwing away, 99.9999, you are not throwing it away. If you find a way to make it cheaper to throw it away, then you can set this threshold to 90%, right? Because then you are throwing away 10%, but you're fine. And overall, you are going much faster. That's kind of the underlying thinking. Like the curve typically has this long tail. And then, so if you want to set it to 99.999%, then you are going 10 seconds. If you want to set it to 90%, then you go 4 seconds. Right? And, yep.
Which one is the better strategy, RLC or RLNC? I mean, it might not be black and white, but what is your take on it?
On RLNC and
versus RLNC? Doing it at network level or doing it at a layer above?
It's different usage. So RLNC is okay. So RLNC is very good for when you have a big thingy that you want to send over, like the whole or nothing. So like the block feels like that. But then you should think that maybe I'm actually better streaming the stuff. So chopping it off to smaller pieces and streaming it. And then RLNC starts to have issues. I've seen that people are using it in streaming contexts. I always had problems using it in streaming contexts. So, and I'm in Zion. So it might not be that good for that. But I think it's RLNC is a nice technique. It has issues, a bunch of them. But it's something to explore definitely. And then RLC, we can just use it for example, in DAS, we can use it to enforce the same thing node so that the sample it takes is just much stronger. It's not taking a cell, but it's taking a linear combination of cells. So when you have to reconstruct, you have a much stronger reconstruction guarantee.
On one of your first slides, you had like different aspects of networking. One of them was privacy.
Yeah.
What do you mean by privacy? Is it like exposing the address of the nodes?
Yeah, it can mean anything, but it can mean that. And it's always like a scale. So we have some level of protection in the system currently, not that high, but we do have something. And sometimes it's the question, because it's not that high, maybe we should throw it away and make the network more efficient. Or maybe we should enforce it, and then we have, so it's part of the compromise space and who we want to protect at the network level.
What's your opinion on that? Like, should we target to still kind of try to keep nodes as private as possible, or?
I don't know, because it's so easy to undo at the moment. So it's like it's always those questions. I don't know.
I'm asking because like we keep investigating and testing the gossip stuff. I think partially, correct me if I'm wrong, but partially because like of this privacy assumption, and if we don't have it, then we could optimize it. How propagation works.
Yeah. So if we throw that away, we can make lower delay, lower bandwidth solutions. My take on that is that we need dual pass basically. We need a system which have a slow pass for private things, and maybe a fast pass for fast transactions. And maybe on the slow pass you are doing ZK aggregation, and on the fast pass you are not doing ZK aggregation. And these have to be kind of go together. But then the dimensions increase, and then you have a problem. So it's privacy, it's ZK aggregation, because ZK aggregation as well is adding a delay, right? It's when you are doing these encodings, then it's always you are adding a delay to the whole process. So, but how you apply it is always like if you want to be really fast, like I want my transaction included in 10 seconds, then ZK aggregation is a bit in the way. Yeah.
Can we do a ZK proof for example, you being a staker and not giving up privacy?
I think there are works on that. Staker.
I think you can be a staker and not give up privacy.
You give a ZK proof that you are a staker, so you can form a very efficient grid.
No, the problem is that you are giving it up when you are generating the traffic. So if I can observe the traffic, I kind of correlate it with the fact that you're a staker, and then I can pinpoint it who are you, because the schedule is somehow public. So you have to hide the schedule, you have to hide a bunch of things. It's just very complicated, and it always comes with delay and bandwidth overhead, like huge. So you have to mask the traffic, you have to add extra traffic, you have to delay everything. It's just not efficient, but it's cool to have it. It's just not the default, I think.
I think for privacy, like that might be a place where node specialization is particularly helpful. For instance, one reason we want privacy is we don't want home operators to be exposed and dust. But if we said privacy is really helpful for like these nodes that participate in censorship resistance, so that they're kind of more invisible to the network, but we have stronger assumptions on nodes that make blocks or that attest. I think I like the idea of having two tabs, like one which is the fast tab that serves like certain purposes, and the other one that is, for slower, more resiliency-oriented services, I think. Yeah,
so it's also on the usage side, you have this like, someone needs fast transactions, someone don't. So you have to think of these trade-offs also in that context.
Can there be a dual role where some entities will say that, okay, we don't need privacy, but will help the network propagate faster?
Yeah, I mean, I think not everyone
I think aggregators could be such roles, so they basically give up privacy, but they can, everyone, instead of just gossiping transactions to each other, they just send the not transaction signatures to each other, they send signatures directly to aggregators, and they do aggregation much faster.
Yeah, like all the other chains are doing it already. Like they gave up a long time ago. It doesn't mean we have to do it. It just you don't need it, because it's so hard and so expensive to do it right. You might want to have these classes separated.
Shaba, thank you so much.
Thank you.